Good afternoon, I'm Mr. H. Thank you for joining me for this video. A very important one because we're looking here at alternating series with regards to the test for alternating series for determining convergence and or divergence. What is a series that alternates? In a very generalized manner, you have A1, you have a minus A2, you have a A3, you have a minus A4, on and on. You have an alternating here between positive or minus, or you could do minus to positive. You could have started here with a minus term and then you alternate with a positive. Example in a very generalized manner, 1 minus 1 over 2, positive 1 over 3, minus 1 over 4, positive 1 over 5, minus 1 over 6. You know we're looking here at a sequence, but if you had a plus sign here in terms of the sum of these, you're looking at a series. But this is alternating series because you have an alternating here between signs. You again could have started here with a minus and do alternating with regards to positive. The series test for this is very interesting. If you have a particular rule, I'm not elaborating what that rule is because it depends on what your series is. You're looking here from n equals 1 to infinity. If each term, succeeding term, an plus 1, this is a term right after the term before it, is always less than or equal to the preceding term, alright? If this is your one condition, and limit as n approaches infinity, this specific item over here, if it zeroes out, you're looking here at a series which is convergent. If you don't meet these two specific items of this alternating series test, then you see divergence. And this applies here for all instances where an, your nth term, is always greater than 0. So what are we looking at here with regards to practical examples? I'll show you 3. That would be perhaps the best way to understand this. If I give you 3 examples and we utilize this test, we can understand convergence. When I have everything written here before you, we are looking at a series because we have plus and minus. We're looking here at everything with regards to sums. If you are to generalize this with regards to a rule, we can. In all instances, we have an alternating here with signs, starting here with a positive. Our rule would be this, 3 divided by, and let's come up with a value here, 6 plus n. And we have to now establish this part right here. N is always equal to 1 going up to infinity. Now we have to do something here with regards to our sign. We're looking at everything starting here from a positive. And you can put it right here, you can put it right here. I'm putting it right over here because I don't have much space over here. I would have something which would look like minus 1 to the power of n minus 1. That would be a rule which would establish that, and we can test it out. If n were equal to 1, I'd have here minus 1 to the power of n minus 1, which is 1 minus 1 to the power of 0 times 3 over 6 plus 1. What do we end up seeing? Minus 1 to the power of 0 is a positive 1. We'll have 3 over 7. If n were equal to 2, we'd have here minus 1 to the power of 2 minus 1 times 3 over 6 plus 2. When you solve this out, what do you get? When you solve this out, you have a minus 1 to the power of 1, which retains a negative. You have minus 3 over 8. And that's how you're going to develop this. So our rule over here looks good to me. Now let's evaluate this with regards to this specific series being convergent or divergent. Your first item you're looking here always is this. Your each succeeding term should be less than or equal to the preceding term, which shows you a trend that you're getting smaller. If you look at each of these, look at any of them and then look at the one before. 3 over 10 should be less than 3 over 9. 3 over 12 should be less than 3 over 11. So each succeeding term is less than the term before. Now that is checked out and that satisfies. Now look at everything here with regards to limit as n approaches infinity. You're applying this limit to your function, which is this. When you're doing that, you really have a 3 over 6 plus n. It wouldn't matter if you really brought this in or not, because what that tells you here, in all instances, you'll always have plus and minus 1 times this function. But you can evaluate this. You're really looking here at, in all instances, 3 over infinity, whether it's plus or minus. You'll be looking at basically a plus or minus 1 over infinity. 3 over infinity, 1 over infinity is meaningless. If you don't like what I'm doing here, you can keep it 3 over infinity, but you're really looking at a 0. In all instances here, you're looking at a 0. This part right over here, plus or minus 1, doesn't really have too much bearing here, because you can be looking at a positive 1 over infinity. You can be looking at a minus 1 over infinity, but they're both still 0. They're zeroing out. So when you're seeing that the fact that these two items are being met, this alternating series is deemed to be convergent, and it would be right. It is convergent. Let's look at this. We have minus 1 to the exponent n minus 1 all over 2n plus 1 from 1 to infinity. It's an alternating series. We have to see if this is convergent or divergent. You don't always have to, but it's good if you do develop a good sequence of numbers. At least 4 is not a bad idea. If n were equal to 1, if n were equal to 2, n were equal to 3, n were equal to 4, what would be your numbers? When n is equal to 1, you have minus 1 to the power of 0, which is just a positive 1, over 3. When n is equal to 2, you have minus 1 to the power of 1, which is a minus 1, and then here you have a 5. When n is equal to a 3, you have minus 1 to the power of a square, which would make it positive. You'd have a positive 1 over 3 times 2, 6 plus 1, 7, and now you're getting the idea, and the next one would be minus 1 over 9. Your series would be 1 over 3 plus minus 1 over 5, 1 over 7 plus minus 1 over 9. These pluses and minuses are redundant. You can just put a minus over there, it doesn't matter, but it is still alternating series. The first test is what? an plus 1 should be less than or equal to an. Each succeeding term should be generally smaller than the preceding term. And would that be the case? If you're looking at this succeeding term, its preceding term is this. 1 over 7 is indeed less than 1 over 5. You're not looking at the signs, but you're looking at the numerical value. 1 over 9 should be less than 1 over 7, and it meets that. What about this limit as n approaches infinity? You're looking at this function. Again, you'll have in all instances a plus or minus 1 based on where you are in your series, but you'll always have 2n plus 1. When you evaluate this with regards to this, you're always looking at a plus or minus 1 over infinity, which zeroes out, and you end up saying that this specific series is convergent, and it would be right because these two items or these two test conditions are met. These are your two test conditions for an alternating series that you need to satisfy for convergence. If any of these does not meet, then you are looking at something which is divergent. And let's look at this as our last question. I already took the liberty over here for the first 4 numbers. I developed the sequence, and then we can put those here with regards to their series. You have here from n equals 1 up to infinity, minus 1 to the power of n, 3n minus 1 divided by 2n plus 1. Again, this always represents your function. The first term here would be minus 2 over 3. You can run these through, it's not hard. Then you'd have a 5 over 5. Then you'd have a minus 8 over 7, and then you'd have a plus 11 over 9. And you know what the test is. The test is made up of 2 conditions. And the condition 1 is this: an plus 1 should be less than or equal to n. The succeeding term should be less than or equal to the preceding term, and you'd have to check that. If when you're looking at both of these, you have a succeeding term that's larger than the preceding term. When you're looking at this right here, you have a succeeding term which is larger than the preceding. You're not looking at the signs, but you're looking at the numerical value of these items. In all instances, it seems like that the succeeding term is always larger than the preceding terms in terms of its numerical value, so you don't really meet that specific condition, which is bad because now we're kind of out of the game for convergence. But what about this limit as n approaches infinity? This function right here, 3n minus 1 divided by 2n plus 1. This right here would just indicate you're looking at a plus or minus being applied with this. You can do like this: 3n minus 1 divided by n divided by 2n plus 1 over n, kind of like a limit evaluation where you're looking for a horizontal asymptote. You end up seeing 3 minus 1 over n divided by 2 plus 1 over n. Limit as n approaches infinity, these zero out, and you end up seeing, rather than your series tending towards 0, it's actually tending towards a horizontal asymptote y equals 3 over 2. So you're never going to zero out. You'll approach a value of 1.5. And you know, with regards to convergence or divergence, that would clearly indicate divergence. So in this specific alternating series, we do not meet both of these conditions. We don't tend towards 0, and we don't have succeeding terms which are smaller than their preceding terms. We just don't see that. And this right here brings us to a divergence case for this alternating series. So I've presented you the general framework for alternating series test. 2 conditions have to be met for convergence, and you can see it's not very complex. And that right there is why I wanted to bring this to you, because it's an important test to know, especially for alternating series. Thank you for watching this video. Have a good day.